Hi class, this is the first video for chapter 5. The second video will cover kinetic molecular theory, and that will be one of my husband's lecture videos. So I already have that posted. I've been having some trouble with my equipment here making these videos, so hopefully this one works out. So let's go ahead and start with gases. Gases are actually the most understood form of matter. And even though their chemical properties can be very different, their physical properties are similar. So let's just talk a little bit about gases. This is sort of a review here. Gas volume changes significantly with pressure. So if we increase the volume, we decrease the pressure. If we decrease the volume, the pressure is increased. We'll talk about that in a minute. We know that solid and liquid volumes are not greatly affected by pressure. So gas volume changes significantly with temperature. So we know that gases expand when heated and shrink when cooled. Think of a balloon. If it's filled with air, if we were to take it outside where it's below zero, that balloon is going to start to deflate or shrink. If I take it back into the house, it will expand again. Volume change is about 50 to 100 times greater for gases than it is for liquids and solids. We know that gases flow freely. They have relatively low densities compared to liquids and solids, and we usually report the density of a gas in grams per liter. Gases will form a homogeneous solution in any proportions. So we say that gases are freely miscible with each other, meaning that they combine together in different proportions. Remember, a gas is a solution, and it, again, is homogeneous, and so you can change the amount of each component because the gas particles are not chemically combined. Think of air, which is mostly nitrogen, oxygen, and a little bit of argon. Of course, there are other gases in the air, but none of the gas particles or gas molecules are chemically combined. We already know from chapter 1 that solids are arrays of particles that are held very close together, and they do not move about one another, whereas liquids, the particles are still very close together, but they move about one another. Gases, on the other hand, the particles are far apart, and they take on the volume and the shape of their container. So let's talk a little bit about gas pressure and how we measure gas pressure. Pressure is equal to the force per unit area, and we know that atmospheric pressure arises because of the force exerted by the atmospheric gases on the surface of the Earth. We also know that atmospheric pressure will decrease with decreasing altitude. So how do we measure pressure? We measure the atmospheric pressure with a barometer. And basically what we have here is a glass tube, and that glass tube is longer than 760 millimeters, okay, and it is closed at the one end. So it's completely evacuated of air, and mercury is put into this tube. And as we see, again, as I said, it's closed at the one end. Mercury is put into this evacuated tube, and this is placed into a dish of mercury. So when the tube is inverted into the dish, some of that mercury is going to flow out of the tube, but you're still going to have a column of mercury that remains in the tube. The mercury in the dish is experiencing the full force of the atmospheric gases, and that will push the mercury up the tube until the pressure exerted by the mercury column downward, and that's going to be due to gravity, So until that pressure equals the atmospheric pressure at the base of the tube. So you can think of the height of the mercury column being a measure of the atmospheric pressure, and that height is going to change depending on the pressure at a given time. How do we measure pressure in the lab? Before we talk about that, let's just think about pressure. For example, a tire. We fill it with air, and that inflates the tire. And why does the tire stay inflated? Well, that's because the gas particles, those particles of air, are constantly moving about. And they're colliding not only with each other, but also the walls of the container. So it's those collisions with the walls of the container that keep the tire inflated. And a little bit later, we'll see how changes in temperature and volume can have a big effect on the pressure. Okay, let's take a look at this figure here. Here we have an evacuated flask, and then we have this tubing. It's a U-tube. And here we see that it's filled with mercury, and here we see that the levels of mercury in both arms of the tube are the same. Okay, so if we were to add some gas to this flask, then what's going to happen is the gas in the flask is going to push down on the mercury level in this left arm. And of course, this mercury level is going to increase. So it's the difference in the height, that delta H, if you will, that allows us to read the pressure of the gas. I'll just go ahead and talk about this now. When you see this delta symbol, in this case it's in front of the height, you might see a delta T. What that means is a difference, and that would be the final height minus the initial height. As for temperature, delta T, that would be the final temperature minus the initial temperature. So that's what that delta symbol means. Now, if I was doing an experiment in the lab, I would use this open-end manometer. I don't think I told you that this was called a manometer. This is one with a closed end, and in the lab I would use an open-ended manometer. Okay, so I would have a flask that has some gas in it. Of course, my U-tube is filled with mercury, but in this case this end is open, so the pressure of the atmosphere that pushes down on the mercury. Okay, and then we have the pressure from the gas. That force is pushing down on this side. So in this case here, we can see that the pressure of the gas is less than that of the pressure of the atmosphere. The pressure of the atmosphere is much greater. So again, this height difference will give us the pressure of the gas. So what we would do is, because the pressure of the gas is less than that of the atmosphere, we would subtract this delta H from the atmospheric pressure to get the pressure of the gas. In this case here, we see that the gas pressure is greater than that of atmospheric pressure. In this case, we would add delta H to the atmospheric pressure, and this would give us the pressure of the gas. So the pressure of the gas is going to be the atmospheric pressure plus this height difference. Let's take a look at some common units of pressure, and here they are. The SI unit for pressure is the Pascal, okay, and the 1.01325 times 10 to the 5 pascals is equal to 1 atmosphere, if you will. The pressure at sea level is equal to 1 atmosphere, or 1.01325 times 10 to the 5 pascals, or 760 millimeters of mercury, 760 torr. We also have pounds per square inch, and we have the bar. In here, we'll be mainly using atmospheres, millimeters of mercury, and the torr, okay? So 1 atmosphere is equal to 760 millimeters of mercury, get that out of there, which is equal to 760 torr, okay? But you might still see these other pressure units elsewhere, so make sure that you're able to convert between them. So here we have a problem at 100 feet below sea level. A scuba diver experiences this pressure here. It's in torr. What is this pressure in atmosphere? Well, we know that 1 atmosphere is 760 torr. We use that as a conversion factor. Torr cancels. That'd be 32.9 atmospheres. That'd be a very high pressure. So I think what we should do now is talk about the gas laws. The gas laws describe the physical behavior of all gases in terms of pressure, temperature, volume, and number of moles. We're going to talk about ideal gases, and these are gases that obey the gas laws. So an ideal gas that exhibits linear relationships among the pressure, temperature, volume, and number of moles. So we see a linear relationship, for example, between volume and temperature, between pressure and temperature, and so on. And that's what we're going to talk about. In reality, there's no such thing as an ideal gas, but most gases will behave nearly ideally at ordinary temperatures and pressures. So basically, your gases, most gases will behave ideally at higher temps, so higher temperatures, and lower pressures. They will begin to deviate from ideal behavior at high pressures and lower temperatures. And we'll talk about that in the next video, or my husband will. So let's take a look at the relationship between volume and pressure of a gas. So in this case here, this is for a fixed amount of gas, okay, so a fixed amount of gas and a constant temperature. So as long as the temperature doesn't change or the amount of gas, the volume occupied is going to be inversely proportional to the external pressure. So we can write that proportionality like so. Again, this is an inverse proportion. And then we would, to make this in a mathematical statement, we add a constant. So we can write this as PV, pressure times the volume, is equal to a constant. And again, this is a fixed temperature and a fixed amount of gas. So what does this equation tell us? This tells us that as we increase the volume, the pressure decreases. If we decrease the volume, we see an increase in pressure. So this is Boyles Law. So let's just take a look here. Here we have a plot of volume versus 1 over the total pressure, and we see this linear relationship. So for example, if I have a piston here with gas molecules, okay, or sorry, a container with these gas molecules, and here I have a piston, okay, this container is 1 liter, and the pressure would be, so the volume would be 1 liter, the pressure would be, we'll make it 1 atmosphere. Now, what happens when I decrease the volume by 1/2? Okay, so I have the same number of particles. I didn't count them, so we have this piston here. So we push the piston down. We decreased the volume And what happens here is the pressure then is increased. Basically, if I start off with 1 liter of gas at 1 atmosphere and I decrease that volume by 1/2, so now I have a volume of 0.5 liters and my pressure is going to double to 2 atmospheres. Okay, so that's Boyles Law. One really good example of Boyles Law is when we breathe. We have the rib cage, which expands and contracts, and the diaphragm is what determines the volume of the lungs. When we inhale, the rib cage will expand and our diaphragm will move downward. So the volume of the lungs is increased, which means there's a decrease of the gas pressure inside the lungs. So the atmospheric pressure then will force the air into the lungs until the pressure inside the lungs equals the atmospheric pressure. When we exhale, this is a reverse of the process. So our rib cage will contract, our diaphragm moves up, and the volume of the lungs is decreased. So the air then is forced out of the lungs because of the increase in pressure. So breathing is an excellent example of Boyles Law. So now let's take a look at another law called Charles's Law. And Charles's Law is the relationship between the volume and the temperature of a gas. So we see here volume versus temperature, and what we see is a linear relationship. Now, the temperature must be absolute temperature, and that is in Kelvin temperature. Notice that if you extrapolate all these lines, when we extrapolate these to the axis, they all intersect here at a negative 273 degrees Celsius. That happens to correspond to 0 Kelvin. Theoretically, at 0 Kelvin, the volume of the gas would be 0, but we have never gotten to such low temperatures. Okay, so again, when you do these problems with the gas laws, you must use Kelvin temperature. So always convert your temperature to Kelvin. So Charles's Law, and now this is going to be at constant pressure, again, a fixed amount of gas. The volume occupied by that fixed amount of gas is directly proportional to its Kelvin temperature. So again, we have the proportionality. We can rearrange this to volume over temperature is equal to a constant. And again, this is a fixed temperature and fixed amount of gas. This is from the one above. I must have copied and pasted that. In this case here, we increase the temperature, and therefore the volume will also increase. If we decrease the temperature, the volume will also decrease. Let's think about it. I talked to you about the balloon. If I'm in a nice warm house in front of the fireplace, I have this inflated balloon, and I take it outside to where the temperatures are really cold, below 0, and what happens? That balloon starts to shrink. And that's because we've decreased the temperature. Everything else remains constant. The pressure and the number of moles of gas, or the amount of gas. Now, when I take that balloon back in the house, where it's nice and warm and toasty, all of a sudden we see it starts to expand. And it turns out that by increasing the temperature, we're increasing the kinetic energy of those gas particles. So the kinetic energy, of the gas particles is proportional to the absolute temperature, the Kelvin temperature. By increasing the temperature, we increase the kinetic energy of the particles. They are going to move faster they're going to collide with the walls of the container with much more force. And the same when I cool it down, if I decrease my temperature, then I'm decreasing the kinetic energy of those gas particles, and they tend to move very slowly, and that's why we see the decrease in the volume. Okay, so this is very important, that the kinetic energy is proportional to the temperature in Kelvin. Okay, so let's see, that was Charles's law. And let's go ahead and look at the relationship between the volume and amount of gas. So at a fixed temperature, so the temperature remains constant, so at a fixed temperature and pressure, the volume occupied by a gas is going to be directly proportional to the amount of that gas. So this is called Avogadro's law. And again, a fixed temperature and pressure, equal volumes of any ideal gas will contain equal numbers of particles, which of course we can translate into moles. So again, we have the proportion between volume and moles. By the way, N is the number of moles. And we can go ahead and rearrange this to the volume over the number of moles is equal to a constant, again, at fixed temperature and pressure. So that is Avogadro's law. Another law that I want to talk to you about is Gay-Lussac's law. Can't remember, L-U-S-A-A-C-S law, also known as Montan's law. And this relates the pressure and temperature. So if we increase the temperature, we see an increase in pressure. And again, that's if the volume and number of moles of gas is constant. Okay, so we can write a Montan's law like so. Pressure over temperature, again, that's in Kelvin, and that is equal to a constant. So this is a direct proportion. Think about an aerosol can. So we have an aerosol can, and it has some pressure, and we have to keep that aerosol can at certain temperatures. If we keep the aerosol can like in the car and it's 0 degrees outside, and you try to spray anything from that can, it's not going to work. That's because the pressure has decreased. On the other hand, if you keep that aerosol can next to a flame, then what's going to happen? It's going to explode. So the increase in temperature will increase the pressure. So that's Gay-Lussac's or Montan's law. Let's go back here to Avogadro's law. And now we're going to talk about gas behavior at standard conditions. Standard conditions, abbreviated STP, that's standard temperature and pressure. That is a pressure of 1 atmosphere, or 760 torrs, 760 millimeters of mercury, whatever pressure equals 1 atmosphere, and a temperature of 0 degrees Celsius, which corresponds to 273.15 Kelvin. Okay, that's standard temperature and pressure. Now we can talk about a standard molar volume. And this is the volume of 1 mole of an ideal gas at standard temperature and pressure. The standard molar volume is 22.4 liters. So here's the key. 1 mole of any gas at STP occupies a volume of 22.4 liters. That could be helium, nitrogen, oxygen, carbon dioxide, air. At standard temperature and pressure, any gas, 1 mole of any gas will occupy a volume of 22.4 liters, period. Okay? You need to know that. Make sure you know this relationship. So it's standard temperature and pressure, 1 mole of any gas occupies a volume of 22.4 liters. So this brings us to what we call the ideal gas law. So we can relate pressure, volume, temperature, and the number of moles. This here is, this R is the universal gas constant. It is a constant. And the value of R is going to depend on the units that are used. All right. The one that I use is where R is equal to 0.0821 liters times atmospheres over Kelvin times mole. Okay, so that's the one I use. When you do problems, you've got to make sure that your volume is in liters, your pressure in atmospheres, of course, temperature in Kelvin, and mole. You can change this. You can actually derive this to where your pressure is in millimeters of mercury. Okay, but let me show you how this constant is derived. What we do is we solve the ideal gas law for R, and that would be pressure volume over number of moles times the temperature. So at standard temperature and pressure, we have a pressure of 1 atmosphere, and the temperature is 273.15 Kelvin. That corresponds to 0 degrees Celsius. And we know that 1 mole of gas occupies 22.414 liters. And we calculate that, and this is what we get. So this is the one that I use. This is the one I'll give you on an exam. Always make sure that your units correspond. Now, the ideal gas law can also be expressed by what we call the combined equation. Okay, so let's take a look at that. We talked about Boyles Law. Okay, so we have pressure times volume, and then we talked about Charles's law, that's volume over temperature, and we talked about Avogadro's law, volume over moles, and this is equal to a constant. Okay, here this includes all of the laws we talked about, including here pressure and temperature for Gay-Lussac's law. What I'm able to do is, because this is equal to a constant, let's say we have initial conditions, we can compare them to final conditions. Let's say we change the pressure and the temperature, we can determine the new volume, okay, by using this relationship here. So we use this when there's a change. So let's just go ahead and do some problems. That'll be the easiest way to do this. So here we have a tank of compressed air for scuba diving, and it contains 8.5 liters of gas at 204 atmospheres of pressure. What volume of air does this gas occupy at 1 atmosphere? We're assuming N and T are constant. So we have volume and pressure. This is Boyles' law, by the way. We have P1, V1 is equal to P2, V2. Again, remember N and T are constant, and those would, N and T, if they're constant, would cancel out on both sides. So now I define the initial pressure. So P1 would be 204 atmospheres. And then I define the volume. So V1 would be 8.5 liters. Let's see. And we're asked what volume of air does this gas occupy at 1 atmosphere. So P2 is 1 atmosphere, and V2 is what we're looking for. I'm going to solve this for V2. So V2 is going to equal P1 V1 over P2. I'll just plug these in. 204 atmospheres. Always use units. That way you'll know if you didn't set things up right or if you make a mistake. And that's divided by 1 atmosphere. And let me put this in the calculator. 204 times 8.5. Okay, divided by 1, of course. That gives me 1734. Forgot to put my 0.0 here. So that's 1734 liters. So we have to ask, does this make sense? So what's happened is the pressure has decreased. So if the pressure has decreased, we would expect an increase in the volume. So yes, that does make sense. I would only want two significant figures here, so I could say 1.7 times 10 to the third liters. This is Boyles Law. Notice my units cancel, and I'm left here in liters. Let's do the second problem. A balloon contains 0.5 liters of air at 25 degrees Celsius and 1 atmosphere of pressure. The temperature is cooled to a negative 195 degrees. What is the volume? So the only thing here that's changing, we have the temperature being decreased, and then we're asked what is the volume. This remains constant. So it's saying the balloon contains this much air at 25 degrees and 1 atmosphere of pressure. All we're doing is decreasing the temperature. What is the volume? So this is going to be a Charles's Law problem. So we have the volume V1 over T1 is equal to V2 over T2. So let's define everything. V1 is 0.50 liters and T1 is 25 degrees Celsius, but we have to convert that to Kelvin. So that's 298 Kelvin. And let's go to V2 is what we're looking for, and T2 is a negative 195 degrees Celsius. Now we have to convert that to Kelvin. So Kelvin temperature is, that'd be a negative 195 degrees Celsius plus 273, and that would be 195 plus 273. That'd be 78 Kelvin. Okay, so we're looking for this. I'm going to go ahead and solve for V2. So V2 is going to be equal to V1 T2 over T1. And then V1 is 0.5 liters times T2, 78 K, all divided by T1, which is 298 K. And we get 0.5 times 78 divided by 298. And I get 0.13 liters. So does the answer make sense? Well, if the temperature decreases, so does the volume. So yes, that makes sense. Let's take a look at this problem. Here we're told the lungs of an average male hold 0.25 moles of air and a volume of 5.8 liters. How many moles of air do the lungs of an average female hold if the volume is 4.6? So here we have 0.25 moles of air and a volume of 5.8. So here we're comparing volume and moles. So I can write this over N1 equals V2 over N2. And let's see here. My initial volume, so V1 is is 5.8. Yeah, do that. 5.8. And my initial number of moles is 0.25 moles. And let's see. N2 is what we're looking for, and V2 is 4.6 liters. So N2 is going to equal V2 times N1 over V1. Okay, So let's see. What we have is V2 is 4.6 liters times N1, 0.25 moles, and that's all over V1, 5.8 liters. Liters cancel, and this would be 4.6 times 0.25 divided by 5.8. That's 0.20 moles. Okay, practice these problems, and again, that was Avogadro's law. So make sure you know the laws as well and what each of those means. Okay, here's another problem. A weather balloon contains 222 liters of helium at 20 degrees Celsius and 760 millimeters of mercury. What is the volume of the balloon when it ascends to an altitude where the temperature is a negative 40 and the pressure is 540 millimeters of mercury? Again, you use the combined gas law when there's a change, when you're given a set of initial conditions and then some final conditions. So in this case here, I don't have to convert the pressure to atmospheres. So let's go ahead and write out the law. We have the volume and the pressure, and then we're asked what is the new volume when it ascends to an altitude where the temperature is a negative 40 and 540. So we have P1 V1 over T1 N1, just using the combined gas law here. That's what I've been doing all along, really. T2 N2. So let's see what's changing here. Where the pressure is changing, the volume, okay, we're being asked what is the volume, and the temperature is also changing. The number of moles remains the same, so that cancels out, okay? And what I'm left with is P1 V1 over T1 is P2 V2 over T2. So I'm being asked what is the volume of the balloon when we change this temperature and pressure. So let's go ahead and define the terms here. So we have P1 is 760 millimeters of mercury, and we have V1 is equal to 222 liters, and T1 is 20 degrees Celsius, which is 293 Kelvin. And then we have P2 is 540 millimeters of mercury, and we're looking for V2, and T2 is a negative 40 degrees, so we convert that to Kelvin and we get 233 Kelvin. So I'm going to go ahead and solve this for V2. So V2 is going to be equal to P1 V1 times T2 divided by T1 times P2. So now I'm just going to plug in. So P1 is 760 millimeters of mercury, and then we'll multiply that by V1, which is 222 liters. Multiply that by T2, that's 233 Kelvin, and divide that by T1, 293 Kelvin, times P2, which is 540 millimeters of mercury. And let me put that in my calculator. 760 times 222 times 233 divided by 293 times 540. And that gives me 248 liters. Notice millimeters of mercury cancel. My temperature cancels. I'm left with liters. So 248 liters. So let's take a look at this one. Here we have a tank. It has a volume of 525 liters. It's filled with 875 grams of oxygen, What is the pressure of oxygen at 27 degrees Celsius? There is no change here. We're not changing conditions. We're being given a volume, a mass, and a temperature. So here we're going to use the ideal gas law. So we're going to use PV equals nRT. First thing we have to do is convert this to moles. So 875 grams of O2, and we know that 1 mole of O2 is 32 grams, and that's going to give us 875 divided by 32, 27.3 moles of O2. So we got that taken care of. Let's see. Our volume is in liters. That's good. And our temperature is 27 degrees, but that would be 300 K. Temperature would be 300 Kelvin. Okay, so I think we're all set. And of course, R, 0.0821 liters times the atmospheres per mole Kelvin. Let's set this up then. What I need to do is solve for pressure. So my pressure is going to be equal to nRT over volume. So N is 27.3 moles of O2. R is 0.0821 liters atmospheres over mole Kelvin. And the temperature is 300 K. We go ahead and divide that by the volume, which is 525 liters. Note how everything cancels. Moles cancel here. Kelvin, that cancels. The liters cancel, and we're left in atmospheres. So we have 27.3 times 0.0821 times 300, and we divide that by 525, and I end up with 1.28 atmospheres. So that is the pressure. So here we use the ideal gas law, and again, there was no change. We were just, told what the volume, the mass of the oxygen, and the temperature was. All we needed to do was solve for pressure. So use the combined gas laws when there is a change in conditions, and the ideal gas law when they're just asking for a pressure, a volume, or the number of moles. So now we're going to talk about rearrangement of the ideal gas law, because in the lab we can use the ideal gas law in order to determine both density of a substance and the molar mass of maybe an unknown substance. It turns out that the density of a gas is directly proportional to its molar mass and inversely proportional to its temperature. So we know density is mass over volume, and moles, okay, which would be N, that'd be equal to the mass, right, over the molar mass. We have the molar mass is equal to the mass in grams, right, over the number of moles. So we just rearrange this where moles is equal to the mass in grams over the molar mass. Okay? So we can substitute then this into the ideal gas law for N. Okay? So we have PV is equal to MRT over the molar mass. Now, we know that mass over volume is equal to density. So what I can do is I can bring the volume over here, right? I have mass over volume, that's equal to the density. So I can rewrite this then as density being equal to the molar mass times the pressure divided by RT. I can determine both molar mass of an unknown in the lab and also the density. Okay? So here I'm being asked, what is the density of argon gas at standard temperature and pressure? So we know the temperature is 273 Kelvin and pressure is 1 atmosphere. Okay, so argon gas, so I have this, I rearrange my gas law. I have the molar mass times the pressure over RT. So for 1 mole of argon gas, I look up the molar mass, and it's 39.948 grams per mole. So 38.948 grams per mole. And at standard, at STP, we have 1 atmosphere. And we divide that by R, 0.0821 atmosphere liters, mole Kelvin. And we multiply that by 273 Kelvin. And we get 38.948 times 1 divided by 0.0821. And I get a density of 1.7 grams per liter. Again, notice that the moles cancel, the temperature cancels, the pressure, atmospheres cancel, and I'm left in grams per liter. Okay, what we want to do now is determine our molar mass from the ideal gas law, and we end up with this expression here. Again, we know that N is M over the mass over the molar mass, and that'll be equal to PV over RT. Okay, and then we solve for the molar mass. We end up with MRT over PV, where the M is mass. So we're asked, what is the molar mass of 1.10 grams of a gas that occupies 0.56 liters at standard temperature and pressure? Remember, I can give you any temperature or pressure, but we just decided STP here. The molar mass is going to be equal to the mass of the gas, so that's 1.1 gram, times R, 0.0821 liter atmosphere over mole Kelvin. Okay, and times the temperature. We know that's at STP, that's 273 Kelvin, and the pressure is 1 atmosphere. Okay, and we have a volume of 0.56 liters. Okay, so we're being asked for molar mass. So let's see, our liters will cancel, our temperature will cancel, our atmospheres will cancel, and we're going to be left with grams per mole. And this works out to be 1.1 times 0.0821 times 273 divided by 0.56, and I get 44.0 grams per mole. These calculations could help us identify a particular gas. Of course, we would use other methods as well, but this would, again, help us identify an unknown gas in the lab. What we're going to do now is look at mixtures of gases. Remember, we know that homogeneous mixtures, the components of the mixture can vary, okay, because there are no chemical bonds between those components. So we know that gases mix homogeneously and in any proportions. So that means that each gas in the mixture behaves as if it were the only gas that is present. So the pressure that each gas exerts in the mixture is called the partial pressure. So, for example, Dalton's law of partial pressures states that the total pressure in a mixture is the sum of the partial pressures of the component gases. And that makes sense. So if you have a mixture of, air, we fill up a balloon with air. So the partial pressure of the oxygen, the partial pressure of the nitrogen, partial pressure of the argon, they're going to be different. But we sum those partial pressures together and we measure the total pressure. Now, it turns out that the partial pressure of a gas is proportional to its mole fraction. So what is a mole fraction? Well, we represent a mole fraction like so. So let's say I have a gas, a mixture that is composed of A and B particles. Okay, let me make that like this: A plus B gas particles. Okay, so a mole fraction is the number of moles of one component over the total number of moles in the mixture. Okay, so for example, if I have, let's say I have ethanol and water. So I have a mixture of ethanol and water. So let's say I have 0.64 moles of ethanol, and I have 0.86 moles of water. Okay, so the mole fraction of ethanol would be equal to 0.64 moles divided by the total number of moles. So that would be 0.64 plus 0.86, and that would be 1.5 moles. Okay, so that'd be the total number of moles. So 0.64 divided by 1.5 will give us 0.43. That would be the mole fraction of ethanol. Mole fraction, notice, is unitless because the units do cancel out, and the mole fraction is always less than 1. So now if I wanted to find the mole fraction of the water in this particular solution, I would take 1 and subtract from that 0.43, okay? And I would get 1 minus 0.43. That would give me 0.57 for the mole fraction of water. And I have to apologize here. I had this N here, and mole fraction is represented by the symbol here. Remember, mole fractions add up to 1. All right, so if you had 4 components, the 4 mole fractions would always add up to 1. And again, it's unitless. We say that the partial pressure of the gas is equal to its mole fraction times the total pressure of the gas. Okay? And if you want to see how that's derived, that's done in your book. So make sure that you understand this. So the pressure of component A, the partial pressure of component A, is equal to the mole fraction of component A times the total pressure of the gas mixture. Here we have a problem. Acetylene reacts with oxygen to give carbon dioxide and water vapor. So we have 2 moles of acetylene and 5 moles of oxygen react to produce 4 moles of carbon dioxide and 2 moles of water. So if we mix the acetylene and oxygen in the correct stoichiometric ratio, so that means we're going to have 2 moles of acetylene plus 5 moles of oxygen. What are the partial pressures of the gases before the reaction occurs? Total pressure of the mixture is 140 millimeters of mercury. We need to determine the partial pressures of each of the gases. So the partial pressure of component A, or in this case here, let's go ahead and the partial pressure of the acetylene is going to be equal to the mole fraction for acetylene, okay, times the total pressure. And then the mole fraction, or the partial pressure for the oxygen, is going to be equal to the mole fraction for the oxygen times the total pressure. So the total number of moles is 7 moles. So let's do the mole fraction for acetylene, and that's going to be 2 moles over 7 moles, and that'll give us 0.28 mole fraction for acetylene. We'll do the same for the oxygen. So the mole fraction for the O2 is going to be equal to 5 moles divided by 7 moles, and that's going to be 0.71. Really, these should be to 1 sig fig. So 0.71, okay, 0.7, this would be 0.3. Okay, so now we can determine the partial pressure of each gas. So the partial pressure for the acetylene is equal to the mole fraction of the acetylene times the total pressure, which is 140 millimeters of mercury. So 0.3 times, is that 140? Yeah, it's 140. And that'd be 42 millimeters of mercury. What I could do is subtract the 42 millimeters. So to find the partial pressure of O2, I can subtract the 42 millimeters of mercury, or of acetylene, from the total pressure. So that'd be 140 minus 42. That'd be 98 millimeters of mercury. And if you miss that, then we could just do the partial pressure of O2 is equal to the mole fraction, 0.7, times the total pressure, 140 millimeters of mercury, and 0.7 times 140 would give us 98 millimeters of mercury. So you can find that second partial pressure easily. Either subtract the first partial pressure from the total pressure, or go ahead and work it using this relationship here. All right, here I have a table that lists the vapor pressure of water at different temperatures. So here it's 18 degrees, for example. The partial pressure of water would be 15.5 torr. So this is in torr. Okay, we'll go back to this table in a minute. Don't worry, this video, it's almost over. So here we're going to talk about a collection of a gas over water. Let me zoom this a little bit. This isn't going to let me zoom. Okay, it's a little bit too big. So we're going to talk about the collection of a gas over water. Sometimes in the lab, this is what we need to do. We might run a reaction and we end up with some insoluble gas product. We would have this set up here. Maybe we're doing a decomposition reaction. Okay, so we have some solid in this test tube and we're heating it to where it decomposes. We might end up with a water insoluble gas product. And so what we do is invert this tube into some water, all right? And basically that water insoluble gas product will bubble through the water, okay, into the this tube here. Okay. So fine, we can measure the pressure, but remember, we're also going to have some water vapor in this tube as well. Again, this is being collected through the water. We collect the gas, and then what we do is we lower this tube here, and we do that in order to make the total pressure equal to the atmospheric pressure. Okay, so we make sure that these levels, okay, this level here is equal to the water level. The level here is going to equal the level in the water that's in the beaker, and that means that the total pressure will be equal to atmospheric pressure. What that means is that the total pressure then is going to be equal to the pressure of the gas, right, plus the partial pressure of the water. And that'd be at some temperature, whatever temperature is given, right? And so what we would need to do is, in order to find the pressure of the collected gas, we would need to subtract the partial pressure of the water from the total pressure. That's when we collect gas over water. That's a very common way of determining the gas pressure when running a reaction. Let's do a little problem here. We have zinc reacting with hydrochloric acid, and we already know that when zinc, solid zinc, reacts with hydrochloric acid, okay, what we get is we'll get some zinc chloride, but it also produces hydrogen gas. All right. So what we do is we run the reaction and we can collect the gas over water. And in this case, the reaction is run at 16 degrees Celsius. The total pressure is adjusted to 0.989 atmosphere. So that's when the reaction is over and we go ahead and equalize the pressure. And we're told that the volume is 1495 milliliters. We need to calculate the partial pressure and mass of the hydrogen gas. The first thing we need to do here is find the partial pressure of the water vapor and subtract that from the total pressure. So I showed you this table back here. So at 16 degrees, the partial pressure of the water vapor is 13.6 torr. So let's go back here. So 13.6 torr at 16 degrees. So what we need to do is convert that 13.6 torr to atmospheres. So we know that 760 torr in 1 atmosphere. 13.6 divided by 760, and that is 0.0179 atmospheres. Find the partial pressure of the hydrogen. We take the 0.989 atmospheres and subtract from that partial pressure of the water vapor, and we end up with 0.989 minus 0.0179, 0.971 atmospheres. So the partial pressure of the hydrogen is 0.971 atmospheres. So we've got that part of the problem done. So now we need the mass of the hydrogen gas. So what we need to do is use our ideal gas law, PV equals nRT. Let's solve for moles. So N is equal to PV over RT. And we have the pressure is 0.971 atmospheres times the volume which is, we're given this in milliliters, so that's going to be 1.495 liters, 1.495 liters. When we divide that by R, 0.02821 atmosphere liters over mole kelvins, and our temperature is 16 degrees, and in Kelvin that is 289 Kelvin. So the number of moles of hydrogen is 0.612 moles of hydrogen gas, and we just need to convert that to grams. So 0.0612 moles of hydrogen. 1 mole of hydrogen gas is 2.016 grams, and that gives us 0.123 grams of hydrogen gas collected. Okay, let's move on, and this will be the last part of our video here. We can also use the ideal gas law and stoichiometry, equation stoichiometry. So in this problem here, we're asked to design an airbag for a car. We know that the bag should be filled with gas that has a pressure higher than atmospheric pressure. Let's make that pressure 829 millimeters of mercury, which is equivalent to 1.091 atmospheres. And this would be at a temperature of 22 degrees Celsius, which would be 295 Kelvin. The bag has a volume of 45.5 liters. So what quantity of sodium azide should be used to generate the required quantity of gas? Oh, I just noticed that here we should have a 3. This is the balanced chemical equation: 2 sodium, 6 nitrogen. That's good. So we need to know how much of this in grams do we need to generate the required amount of gas. So we use our equation stoichiometry. The first thing we need to do is find the number of moles of nitrogen. So we can do that again using the ideal gas law. So N is equal to PV over RT, and our pressure here is 1.091 atmospheres, and the volume is 45.5 liters, and that's divided by 0.0821 liters atmospheres over moles Kelvin, and that's multiplied by the temperature, 295 Kelvin. So the number of moles of nitrogen gas will be 2.0496 moles of nitrogen gas. So remember, in order to find out the amount of this, I need the number of moles of the gas. And the only way I could do that was using the ideal gas law. Now I know the number of moles of gas, and I'm going to go ahead and give this 3 significant figures here. So now I use my equation stoichiometry in order to find the amount of sodium azide. So we have 2.0496 moles of nitrogen gas, and our mole ratio is 3 moles of nitrogen to 2 moles of sodium azide. Then we convert that to grams, so 1 mole of sodium azide would be 64.99 grams, and that'd be 2.0496 times 2 divided by 3 times 64.99, and we would need 88.8 grams of sodium azide. Okay, So this showed us that, yeah, when we have a chemical reaction that involves gases, that we can find the amount of solid or liquid by using the ideal gas law to determine the number of moles of a gas. Well, that's it for this video, and Dr. Mundell will be in the next video, and he will finish up this chapter. So everybody have a great day. If you have any questions, let me know. Also, remember, I am on Blackboard Collaborate in the mornings at 10:40.